Thank you for choosing to view this video clip. The Aspen project is planned to produce an online educational system that will allow students and scientists to keep abreast of the rapid developments in laboratory technologies and their application to research and testing. As you will see, this project fills a growing gap between the science education available in undergraduate and graduate work and the knowledge needed to take advantage of the tools of modern laboratory science. Vendors are continually developing products to improve the way laboratory work is done. If they aren't used properly, they represent missed opportunities and can potentially produce faulty data. Better educated people will do better science, and that will result in more effective research and testing programs. If people aren't educated in these technologies, the results can be wasted resources, inaccurate data, and research programs that don't reach their goals. During the next few minutes, we'll give you an overview of the challenges that lab professionals will face when working with the tools of modern science. We will also present the need for an educational facility that lets them learn new concepts and skills as technologies and methods advance, in a way that allows people to learn those skills as needed, when needed, as part of their work. This applies to all sciences, including chemistry, clinical work, physics, biology, mathematics, as well as engineering and information technology in support of laboratory work. If you were to do a search on growth rates for scientific knowledge, you would find a wide range of opinions. A consensus would show that scientific knowledge is growing rapidly and in some fields exponentially. This means that those entering scientific work have to learn a lot more to be productive, and that the need for learning never stops. One of the frustrations of modern education is that the amount of knowledge that students need to learn is expanding, while undergraduate requirements are changing slowly, if at all. This leaves a growing gap between what students at all levels need to know and what they have time for in formal coursework. This need to learn will continue throughout their lives as new instruments, data handling techniques, and scientific fields develop. The most dramatic changes in laboratory work can be found in the tools and methods used to carry out research and development, as well as testing in industrial and healthcare applications. Robotics provide better and faster methods of preparing samples for analysis and evaluation. Paper laboratory notebooks are being replaced with electronic versions that offer better documentation of experiments, searching, archiving, collaboration, and management of intellectual property. Let me begin by putting the need for education in perspective through a personal story. I graduated from college during the 1960s, taking all the standard chemistry courses plus some extras that included polarimetry, paper chromatography, electrodeposition techniques, basically what a college chem lab at that time period could afford. I also worked with one of my professors building a homemade gas chromatography system. Chromatography is one of the most widely used instrumental analysis techniques due to its simplicity and the ability to isolate the components of mixtures. It can help determine the identity of a component and the amount of material present in the mixture, and is employed in chemistry, life sciences, environmental, food and beverage industries, oil and gas, to name just a few examples. The instrument we constructed used quarter-inch tubing packed with Tide detergent and Galmac thermal conductivity detectors, using helium as a carrier gas. It worked, and we spent time learning how to do separations and look at the effects of temperature and so on. Although it was a very simple device and a far cry from commercial systems, it turned out to be a very useful experience. After graduation, I went looking for work and was interviewed by a chemical company that manufactured plastics and polymers. They were looking for someone to work in their analytical laboratories in an entry-level position. During the interview process, I was taken on a tour through 2 labs. The first one felt very comfortable since it was filled with the same types of equipment I had worked with in my classes. This was where wet analysis and some sample preparation was performed. The second lab blew me away. It was loaded with instrumentation that for the most part I had never seen in any of my coursework. We had studied spectrophotometry using simple manual spectrophotometers, but nothing like this. There were infrared spectrophotometers, spark emission spectrometers, UV visible instruments, and pyrolysis equipment. Fortunately, there were also a number of chromatographs, but these were nothing like the home-built equipment that I had worked with in school. Thankfully, the only instrument they had asked me about during the interviews were chromatographs, so at least I could talk intelligently about something. I was hired and spent a lot of time asking lots of questions, learning about the instrumentation at night, and coming in early to get some experience working with them. Eventually, I became proficient with all the tools in the lab, and later extended my expertise to things like atomic absorption and thermal analysis. Students coming out of undergraduate work today are in very similar positions when they go into research and industrial laboratory work. Their science classes give them a basis for understanding the science that they're going to be doing, but in many cases does not teach the details of using the equipment that they might be working with, even if the schools have access to it. There is also a limit to how much can be packed into an undergraduate or graduate program. The rapid development of new scientific fields puts added pressure on academic work. The situation has become more acute as traditional methods have been replaced with instrumentation and robotics, both controlled by software systems. This pushes people in science into specialization with a narrow focus and a lack of awareness of the scope of information technology applications for lab work. Vendors are building in ease-of-use facilities. However, at times these facilities mask the care that has to be paid in settings, testing, and verifying parameters for data acquisition and analysis. We have to be careful that we don't move into push-button science, relying on vendors' default settings and not examining the data closely enough. There are few, if any, well-organized courses in the field of laboratory automation, informatics, and computing. Most educational programs are provided by vendors, usually product or technology specific, centering on their commercial interests. On-the-job training, which due to time constraints is usually limited to what is needed to get a task done, avoiding the underlying theory of the technologies. It stresses what to do mechanics rather than understanding, at least in the short term. And finally, conference short courses, some provided by vendors, some by industry experts, but only available at the meetings with no long-term coordinated program. If that weren't bad enough, consider the same people when they are faced with working with modern laboratory informatics systems, computer systems running software that they haven't seen or heard about but are expected to use. Laboratory information management systems, electronic laboratory notebooks, scientific data management systems, lab execution systems, and computer-controlled instruments are just a few examples. The combination of instruments and computer systems is particularly troublesome. Analysts should understand the instruments, how they work, the nature of the data, and how to analyze it. The computer systems tied to the instruments allow the users to defer some key steps and decisions to the computers and often trust whatever results the computer generates. The data systems are there to do the data collection and analysis, but before they are put into production, the users have to verify their operation, and they may not have been trained to do that. While the technology is rapidly developing, the technical capability of those working in labs, and in particular those coming into the field, has not kept up. This statement from American Laboratory reads, "Even today, the instruments are often more sophisticated than the average user, whether he or she is a technician, graduate student, scientist, or principal investigator using chromatography as part of the project." And that citation isn't alone. From a 2005 article, we can see, despite a lot of exposure to computerized data handling, however, many practicing chromatographers do not have a good idea of how a stored chromatogram file, a set of data points arrayed in time, gets translated into a set of peaks. The background on the screen shows a grid whose bottom axis is time beginning in 1970, and whose vertical axis shows 5 key laboratory functions: document management, experiment execution, record keeping, sample tracking, and instrument data capture. Now we'll map out the development of 4 key technologies, 3 we've noted in this presentation. The fourth is scientific data management systems, used for managing lab data files. Notice when the different technologies appear on the chart and how rapidly they expand their complexity. These technologies are not used in isolation, but often in combination, each meeting particular needs. One goal, yet to be realized, is the integration of products to smooth the flow of information. Understanding what these technologies are, how they contribute to lab operations, what they are or are not capable of, is essential to your students' success in laboratory work. Not only do people need to be better educated when they come out of school, they need access to continued, ongoing educational programs to keep up with new technologies. Education is not just for laboratory professionals, but for those who support their work as well. The increasing reliance on information technology means that IT professionals need to understand how lab systems are used and how to support them. In particular, they need to understand the regulatory environment to ensure that regulations and standards are met. The education we provide will help IT and lab professionals work together and relieve a common and persistent problem in the industry. The purpose of the Aspen project is to give scientists, technicians, and information technology specialists a place to get the education they need when they need it, to fill the gap between what is available in schools and what they need to be fully productive researchers and lab professionals, meeting the needs of the fields that are rapidly developing. It is planned as an online system that allows anyone interested to look at and take courses that can meet their educational needs. Some material will have wide application. Others will focus on more narrow applications. We'll build the system structure around the elements of Laboratory Technology Management Program developed by the ILA. The various sections of that structure cover management issues including planning, project management, and regulatory issues. The classes of laboratory automation implementations looks at 3 types of informatics and automation technology styles and how the nature of laboratory work will change as computer-based technologies and automation are used. Experimental methods looks at what happens as laboratory work shifts from manual to automated systems and how these experimental techniques have to be adjusted to work effectively with these technologies. We also cover the technologies themselves, the application of information technology techniques to laboratory work, and the basis for systems integration. Please view the material on the website for more details, and thanks for watching this video clip.